All right, let's take a moment and look at some equilibrium calculations. I think the best way to do this is to just look at a couple and go through them. All right, these are simpler calculations. We'll get into something that's a little bit more complex in a little bit. So let's look at this reaction. We've got a mixture of hydrogen and nitrogen in a reaction vessel, and it's allowed to attain equilibrium at 472 degrees Celsius. The equilibrium mixture of gases was analyzed and found it contained 7.38 atmospheres hydrogen, 2.46 atmospheres nitrogen, and 0.166 atmospheres ammonia. From these data, calculate the equilibrium constant Kp for the reaction. All right, well, let's write the expression for Kp first. So if you remember, equilibrium constants are the products over the reactants, concentrations raised to the coefficients. It's a Kp. We're dealing with gases, so we're going to use partial pressure. The only product is ammonia. I'm going to square that partial pressure over the partial pressure of nitrogen and then the partial pressure of hydrogen to the third power. I'm given all the values for those, so let's put those values in. So I have 0.166 atmospheres. It doesn't matter because my equilibrium constants don't have units. My pressure of my nitrogen, 2.46, and the partial pressure of hydrogen is 7.38 to the third power. So putting that in my calculator, I get Kp is equal to 27.9. Okay. All right, let's look at another problem. Oh, I hid the answer on myself. All right, so here I've got an aqueous solution of acetic acid found to have the following equilibrium concentrations at 25 degrees Celsius. Calculate the equilibrium constant Kc for the ionization of acetic acid at 25 degrees Celsius, and it gives us the reaction. Please pause the screencast and try to figure this out on your own. Going through the steps, we have Kc is equal to the product concentrations. That's the hydronium ion times the acetate ion over the acetic acid. Okay. Everything is just to the first power because there are no coefficients, meaning the coefficients are just 1. Plugging in the numbers that are given up here, 5.44 times 10 to the negative 4th. For my acetate ion, same thing, 44 times 10 to the negative 4th over the concentration of the acid, 1.65 times 10 to the negative 2nd. If I plug those answers in, I should get 1.79 times 10 to the negative 5th. What does that tell you about this equilibrium? Do the reactants predominate or do the products? Because I have that negative exponent, I have something much smaller than 1, so it means that my reactants predominate. All right, now we're going to get into a little bit more complex of a problem, just a little bit. All right, so I've got hydrogen and iodine reacting to form hydroiodic acid. It tells me I have a closed system, initially containing 1.0 times 10 to the negative third molar hydrogen. I've got some iodine in there as well, and it's allowed to reach equilibrium. So analysis of the equilibrium mixture shows that the concentration of the hydroiodic is 1.87 times 10 to the negative third molarity. And it tells me to calculate Kc. Okay. Well, you know that Kc is the concentration of your hydroiodic squared over your concentration of your hydrogen times your concentration of your iodine. Here's the problem. The concentration for the hydrogen and the iodine, are at the initial conditions. So initially, that's how much of this and this I have. But in order to calculate that equilibrium concentration, or that equilibrium constant, I have to have the concentration of the products and the reactants at equilibrium. Well, let's fill in a table. What do we know? Well, we know that initially I have hydrogen and iodine, and I don't have any hydroiodic. I know when that system is allowed to come to equilibrium, I then have 1.87 times 10 to the negative third concentration of my hydroiodic. Okay. Do I have enough information? Oops. Do I have enough information to calculate what the concentration is of the hydrogen and the iodine at equilibrium? Well, if you think about it, where did this hydroiodic come from? Well, it came from some of the hydrogen and some of the iodine reacting. Okay. So the change was an increase in the hydroiodic. Where did it come from? Well, it had to come from the hydrogen and the iodine. Remember that the balanced chemical equation was H2 plus I2 in equilibrium with HI. So for every 1 mole of my hydroiodic, I should say for every 2 moles of my hydroiodic, I'm going to use 1 mole of my hydrogen and I'm going to use 1 mole of my iodine. So this change is really from the stoichiometry of the equation. Okay. Then at equilibrium, I'm going to have the initial concentration. Okay, this initial concentration minus the change, and this is my new equilibrium concentration. Now I can just plug those into the equilibrium constant and come up with a value for that constant. These tables that we use to come to this, okay, it is the, it is the initial concentration, the change, and then at equilibrium. These are referred to as ice tables. Okay, these are referred to as ice tables. What happened initially? What was the change? And what was the concentration at equilibrium? And they are based on stoichiometry. Okay. So, Switching gears just a bit, let's talk about the reaction quotient. This is called Q. Actually, you know what? I would like to stop I'd like to stop right here. We'll pick up here at the next one.